Today, I'm going to start with domain and range. We have a few different topics we're going to look at today. We're going to look at domain and range. We'll look at increasing and decreasing behavior. We will look at asymptotes, discontinuities, a few different things, but we're going to start with domain and range. With domain and range, the way I taught you in this past, if you were given a graph, the way I taught you in the past is I said I'd recommend using what I called trash compactor technique. I don't know if you remember this, but why is it not? Come on now. Where's my little trash compactor? Let me try this one more time. There we go. A trash compactor, if you've ever, I don't know, watched a dumpster pick up your trash, they throw the trash in and then the walls close in on it. They smash it all to make more space. So all the trash gets smashed together to make more space. And that's basically the idea. When I find domain and range, what I'm doing is I'm smashing out, when I find domain specifically, I'm smashing out the range. That's what I'm trying to do here. When I flatten out this graph, I'm going to remove the range. It's only going to be the domain left over. So I'm going to call this first piece the red piece here. And so this red piece is all going to get smashed to the x-axis. So like this solid dot, for example, is going to go right here. So this solid dot gets moved down there. This open circle goes there. They'll be connected. I'm just making it flat. I know it's a parabola up here, but it's getting flattened out right now. So it looks like that. This piece goes on and on and on. And then I come over here to this arrow. And I got a question for you. Is this arrow heading directly down, meaning it needs to just stop right there? Or is this arrow going diagonally, meaning it's going to go down and to the left? What's the case here?
Down and to the left.
It's going to continue to go down and to the left. So what that means is when we flatten it, this will continue to go to the left further and further. So I'll put an arrow on this end. So there's the red piece for domain. Sorry, I'm going to make a better little circle there. It's easier to tell. That's open right there. Okay, so now we'll take a look at the second piece. The second piece I'll do in blue. It starts with an open circle. It continues on. And I notice, okay, as this one goes off the screen, is it going diagonal up and to the right? Or is this one going straight vertical up? What's happening as it goes off the screen? That's right. It goes up, but it never actually touches 4. Because of that, it's kind of like an open circle. I know it doesn't have an open circle on it, but that's basically how you treat it. It's like an open circle. So it won't hit that point, but it will be connected in between. Now this next piece, I'll do the next piece in purple. I'll use P for purple. It has the same concept. It goes up, but it never actually touches the 4. So it's also going to be like an open circle, but it's going to continue on forever to the right. So there's our domain. When you look at this domain, it does go left forever. It does go right forever. Is it filled in everywhere in the center? No, we have breaks. What type of break? Not what type of breaks. I'm sorry. Yeah, I'll ask that question. What type of break is that right here? Is this a removable break, a jump break, or an infinite break?
Removable.
It's a removable. Yeah, this graph, the domain is broken at this removable discontinuity right there. So we should have a break at the value -3. So when I scan my options, I should have a break at -3, which all of them look like they have a break at -3. I do see these say -8. That's bogus. So those two are out. So we do break there. As I continue on, at this jump discontinuity, and I put that arrow in the wrong place. This up there is the removable, right there. At this jump discontinuity, does my domain actually break? No. My domain remains intact, so I'm not going to break it at 3. For that reason, this one's out, which means this answer has to be the correct answer. But I am broken at 4. What type of discontinuity would you call this break here where the graphs go to infinity? That's right. That's an infinite discontinuity. That right there is an infinite discontinuity. And I didn't put my jump on there. This one was a jump discontinuity. But the jump did not break the domain, but it was a jump discontinuity. All right. Questions on this one? I didn't do the range. Whoa. But I could do the range pretty simply by following the same. What is going on? Where was clear ink? Let me try this one more time. Clear ink. Okay, if you're going to do range, the only thing you would do differently is you would smash it to the y-axis. So we'll figure out on the range that this is all reals pretty quickly. When I smash to the y's, nope. When I smash this to the y-axis, you'll find out this red piece goes down forever. So it starts there and it goes up, 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 up all the way till you have an open circle there. The graph continues to go up. It comes to this point, which is basically like a dot. And then it comes back down and it fills it in on the other side. So what's more powerful, an open circle or a closed-in circle? Closed. So this is filled in all the way. So right now the range is like from, I don't know, negative infinity to positive 15 or so with the bracket. But then when I come in with this next piece, which I think I did blue last time, you would put an open here and it goes up forever. But because the red is solid going through it, the red fills it in. It's basically the same thing as having a point there. So for that reason, it's all reals. And you don't even have to mess with the purple piece. It's all reals already. All right, so that would be number 5. Let's see our statistics on that one. Oops, wrong document. Discontinuities. Oh, I'm too far down. Where is it? There it is. We got this one correct only a third of the time, 34%. So that one, hopefully we can improve on a little bit, just from remembering to use trash compactor technique. All right, well, I'll come back to this one. That one's roots and extrema. I'm going to come back to that. I'm looking for domain and range. So I'm going to skip 12. Here we go. Number 18. What's the domain of this function? Well, I'm just going to get a blank graph. So to get a blank graph, I'm going to erase the crazy letters there at the end of my address bar and get a just brand new graph like that. And I will type this in. F of x equals x divided by x squared plus 3x. So there's my graph. Now, Desmos almost makes domain cheating. It really does. It makes it so simple, it's almost cheating. Why do I say that? Because if you use their table with you, if you hit edit list, hit table, you can almost see any values that would ever be a break. So I'm looking down the list. This shows me that I have breaks. Every one of them shows a break at -3. And these last two options have a break at 0, helping you interpret this. Desmos would, if you just type in the values, it'll let you know if it's broken or not. So does my graph break at -3? What does undefined mean? That means it doesn't exist there. It's broken. So it has a break at -3, and this has a break at 0. So that's why I say Desmos makes this so easy. If you have an equation for domain, it makes domain so simple. I can eliminate those two right there. Next, if a graph is broken, it cannot be equal to it. So these brackets mean equal to. So this one's out as well. For that reason, this is my answer. Now, I'm going to pause and go show you some algebra now. Let's do some algebra. The way to remember domain, it follows 3 rules. So we talked about this a whole lot this school year, especially during chapter 1 and 2. The domain rules were this. Number 1, you cannot divide by 0. Number 2, does anybody remember number 2? Has to do with the square root. You cannot square root a negative. That means you have to be greater than or equal to 0. And third, this was chapter 3, a logarithm must be positive. Those are our 3 domain rules. As you look at this problem up here, which rule, otherwise it's all reals. When I look at this one up here, what rule might I possibly be breaking? Rule 1, 2, or 3? Do I have division? Do I have a square root? Or do I have a log? Division. So I'm going to compare this using rule 1, that it cannot equal 0. The denominator cannot equal 0. So my domain, all I would do is solve that x squared plus 3x cannot equal 0. That's how you would solve the domain here. And what I would do first, these are sharing something. What's shared on both of those? X. If we did a GCF, we'd see that we have x times x squared plus 3. Not x squared, I'm sorry. X plus 3 cannot equal 0, so I did a GCF. And now I'm multiplying with the product of 0. The 0 product property from Algebra 2, 0 product property says that if you're multiplying and you're getting a product of 0, the only way to do so is that either the front factor is 0 or the back factor is 0. Something equals 0 in there. And so either you just said it, since this does not equal, say x cannot equal 0 and x also cannot equal, because the inside lies, a negative 3. So x can't equal 0, x can't equal negative 3. That's where those numbers came from. And since it can equal it, it's a parenthesis. So it's all reals except for those 2 places, which is the same thing written there. Does that make sense how I did that algebraically? All right, let's look for our next domain and range. Here it is, the next one. All right, on this problem, again, I'm going to use trash compactor technique. It asks for the domain and the range. So for domain, this is a reminder, what we'll do is we will use trash compactor technique. So I'll take this and this. And so for domain, you smash to the x-axis. So I'll smash this one this way, this one this way. I'll call this the red piece. The red piece goes from here to here. Really simple. This one's going to be the blue piece. From there to there. Really simple. And the last one will be the purple piece. There to there. Question for you, this domain. Do I have any breaks in the domain? I see an open circle and a closed circle in the same spot. What happens with that? If it's open and closed. The closed fills in the open. So this domain is all reals, which means this one's out, this one's out. It's one of these 2. So now we switch over and we say, okay, what about the range? So when I slide this one over, and I slide this one over, I can now find the range. So the red piece gets smashed in this way, and it creates this this symbol here, or this. When I strip away the domain, it just becomes a flat line like that. The blue piece would go up. That would be like a closed dot, and then it goes down. So you can see this is all connected solid. So it's from -5 up to infinity, all reals, which both of them have that. So now it comes down to the purple. What happens to the purple when I smash this in? I have an open circle, but what do I do with the rest of this as it gets smashed in? Okay, so what do? Do I leave it open like this?
You close it because the rest of the line is closed.
All this line is closed. So all the way down, that's closed, so it'll actually fill it in. And so for that reason, it's closed. So does that mean the -6 needs brackets or parentheses if it's just a dot? Needs brackets. So C is correct, D is incorrect because of that portion. Now, I think that's all for domain and range. Yes, it is. So now you have a DOL to try. I want you to open up and go to number 3 and try this one. Pay attention to what you're supposed to find. It says, what is the range? Make sure you find the range of that function.